Right, well, thanks very much, Suraj, and thanks so much for the introduction and the opportunity to give this seminar in this new webinar series. I'd like to talk about the work we're doing on our Indicators of Climate Risk project, funded, as Suraj mentioned, under the first wave of the Climate Resilience Programme. The project's been led by us at the University of Reading. It involves UKCH and also involves input from Jason Lowe, primarily wearing his Leeds hat. What I want to do is talk through 5 different aspects of the project. I want to talk about what the objectives are, why we did the project, some core principles about how we did the project and why we did things the way we did. I want to talk about methodology a bit, because one of the things that we discovered is that the way you do things is really important, and the specifics and the mechanics of how you do that are really quite important in determining what you can do and how you can interpret your results. As will become clear, we've calculated changes in risk under a wide range of indicators, so I'm not going to go through indicator by indicator and tell you what the answer is. I'm going to give some overview of our results, both results in terms of how risk might change in the future and results that have implications for where we think about how we assess and manage risk. And I want to just finish with some key conclusions. So, as Suraj has mentioned, the Climate Resilience Programme has really got 3 broad aims. One is characterising and quantifying risks. Second is managing risks through adaptation. And the third is about climate services. And our project fits really clearly within the first broad objective of the Resilience Programme. We're seeking to characterise, quantify climate-related risks to the UK over the course of this century. We've got 4 specific project objectives, and the first is to look at policy relevant indicators of climate risk. I'll expand on what that means in a moment. And secondly, we wanted to look at these indicators with different emissions pathways, low emissions, high emissions, and so on. And thirdly, we wanted to look at these indicators at different levels of warming. What are the impacts at 2 degrees or 3 degrees or 4 degrees? And fourthly, we want to produce a relatively small number of spatially coherent multi-sectoral scenarios. Now, I'm not going to be talking about that today because that's still work in progress, and I'm going to concentrate on the first 3 of our project objectives. But essentially, we're defining policy relevant indicators, we're calculating them at different rates of emissions, and we're calculating them at different levels of warming. So the point of the project really was to try and understand current and particularly future risks. So we're looking at how risks might change in the future on the grounds that if we want to improve resilience to climate change in the UK, we need to know how these risks will change. When we looked at the issue and when we were constructing the proposal and since, we found actually surprisingly little consistent information on how risk might change in the future across the UK, despite the availability of a long history of UK climate projections and quite a history of UK climate research and impacts. There's very little across the UK scale that presents climate information in terms that are most directly relevant to policymakers at national and local levels. So there's relatively little information out there. Not nothing, if you see what I mean, but relatively little. And meanwhile, there's a big demand for evidence. The third climate change risk assessment, which Suraj has just mentioned, is looking at what future risks might be in the UK. National policy on climate change adaptation and resilience is emerging and developing in the UK. All sorts of reasons, COP26 being one, the Committee on Climate Change criticism of the lack of progress in UK adaptation being another, and there's all sorts of reasons why national policy is developing on enhancing resilience. And of course, over the last year or so, many communities at different scales have declared climate emergencies, and the sense we get is that they're often looking for information on what the emergency is going to look like in terms a bit more locally relevant, or a bit more relevant in terms of impacts and consequences rather than just temperature and rainfall. So the point of the project was to provide information to help enhance resilience. We spotted a gap in consistent information, and there's increasing and emerging demands for this information. So the project has three core underlying principles. The first one is that we're not trying to estimate the impacts of climate change in terms, for example, of the numbers of people affected or the average annual loss or things like that. We're trying to calculate indicators which are relevant to help inform policy. I'll talk about what the distinction between indicators and impacts a bit more in a moment. The second point about the project is that we've endeavoured to consult and engage with a wide range of stakeholders, government and to a lesser extent so far, private sector, across the course of the project, because we want to produce information that's directly relevant to policy decisions. Again, I'll expand on what we've learned from that process in a moment. And the third key principle is that we build very strongly on the new UKCP 18 climate projections. That other sources of information are available, but we do use UKCP 18 partly because it's a great new resource and partly because it'd be difficult to come up with any sort of guidance or information that uses anything other than UKCP 18 at the moment, because UKCP 18 and its predecessors are essentially regarded as best practice within government and lots of organisations. So we've built very much on the UKCP 18 climate projections. So climate risk, first of all. An indicator is not a measure of impact, it's a representative of some type of consequence. So for example, in economic terms, change in GDP is an indicator of economic activity. It doesn't mean anything necessarily directly, it's not a measure of change as such, it's a measure of direction of change and change in characteristics of a system. So an indicator is a representative of some type of consequence, for example, for policy. It might be, for example, the frequency with which some policy relevant threshold is exceeded. I'll give some examples of that in a moment. Now, Suraje mentioned this at the beginning, but we see strongly that risk is a function not only of the change in hazard and resource, but also change in exposure and change in vulnerability. What we're doing in the project is concentrating very much on the indicators of change in hazard, which many people will be familiar with this diagram from the IPCC SREX report. It's known as the propeller diagram, which illustrates how climate risk is a function of hazard, exposure, and vulnerability. We're concentrating very much on the hazard side. We're not looking explicitly at exposure in terms of number of people or vulnerability in terms of the ability of groups to respond to a pressure. But we think that most of our indicators, not all, but most of our indicators, because they use thresholds that represent some important policy level, they implicitly have some aspect of exposure and vulnerability wrapped up in them. So although we're looking at measures which start by looking at climate hazard and the climate resource, the thresholds and the criteria and the indicators we're using are ones that have been identified as being meaningful. Therefore, we can interpret most of them, not all, but most of them as measuring risk, even though we're not explicitly incorporating exposure and vulnerability. The risk is in the thresholds and the variables that we define. So that's what we're doing. We're calculating indicators of climate risk. And one thing that struck me this morning when I was looking over the presentation is that the title is ever so slightly misleading. The title of our presentation is Indicators of Changing Climate Risk in the UK. In fact, we're not using these indicators to monitor how risk is changing now. We're using these indicators to monitor what risk might be like in the future. And that's an important distinction that I hadn't really picked up or registered until reasonably recently. And that's something we might want to discuss later on about the role of indicators in measuring and monitoring change. We're looking at indicators to describe how things might change in the future, not how they're changing now. So here we've got our summary list of our high-level indicators. So they cover a wide range of sectors. I haven't defined here what the specific thresholds are. Some of these thresholds are, the thresholds are variably defined. Some of them are nationally variable, some are more regional, and so on. And there are different variations on these indicators with different thresholds. The point is to illustrate that we've got a range of indicators of future climate risk in different sectors relevant to particular policy related issues. I just want to highlight that the hydrological indicators that we calculate are calculated by UK Centre for Ecology and Hydrology, using their grid-to-grid hydrological model. So they're very complicated, very locally tuned, really very reliable. The other indicators are calculated at a coarser spatial resolution because they're fundamentally much more simple than the hydrological indicators that CH are calculating. So that's our list of indicators. We can talk about specifics, what the specific thresholds and so on might be in discussion at the end. One point I'd like to point out now is that there are some notable emissions, and we're aware of these. There's nothing to do with the coast and sea level rise, that's deliberate. There's nothing to do with storms, that's deliberate. There's nothing to do with extremes of short duration rainfall, that's deliberate. There are other projects in the resilience program that look at that. And we don't really look at indicators that are relevant to the natural environment. Again, that's deliberate. We've narrowed down the focus, but the point is we've identified a range of indicators covering a range of sectors, ones that we can calculate with UKCP18 climate projections. Second key principle is one of stakeholder engagement. This has led to four enhancements to the project. One is it relates to details on those specific indicators we saw in that previous table. So information about what those indicators should be, what the policy relevant dimensions are, what the thresholds may be. That's been very helpful. We've identified some new relevant sectors. So for example, in the original proposal, we didn't include wildfire. We do now. Identified that that was a sector with a big demand for information and a bit of an information gap. Over the last year or so, government policy has shifted a bit towards interest in particular pathways of climate change. So 2 and 4 degree pathways rather than impacts at 2 and 4 degrees. That's something that we've identified by discussions with stakeholders. And we've also been aware of an interest at a much finer spatial scale than we thought in the first instance. So looking at local resilience for example. So the stakeholder engagement part of the project has given us some really useful extra insights into what we should be calculating and what we think is going to be relevant for a whole range of different policy users. Third key principle, as I mentioned, is that we're using very heavily the UKCP climate projections. In practice, we're using the top 3 segments of the UKCP18 trivial pursuits pie. We're using the probabilistic projections, we're using the global projections, and the regional projections. Each of these have got different characteristics and different qualities. The probabilistic projections, for example, are meant to characterize the full range of change. They're available for different rates of emission. The global and the regional projections are much more, in a sense, specific. They're much more detailed. They've got much stronger spatial coherence. So looking at impacts in several places, you'd probably need to look at the global and regional projections, but they only span a particular part of the space. So we've used all these UKCP18 climate projections, and we've also constructed our own subset of pathways that are consistent with 2, 3, and 4 degree targets, essentially by extracting members from the probabilistic projection set. So that's our 4th set of climate projections. We've not used all of these for all our indicators for technical reasons that we might want to discuss at the end, but this is the family of climate projections we've used. As I say, the different UKCP18 products have got different purposes and different strengths and different challenges, and we've used all of these and we're combining them to produce our estimates of impact. One thing that is worth noting, and one thing that has relevance that we'll see later on in the project, is that the subset of global and regional projections, the global and regional strands that the UKCP18 call them, they have extra information, they have spatial coherence, they have lots of information that the probabilistic projections don't have, but they don't necessarily span the same range of uncertainty as the probabilistic projections. And this is illustrated in this slide here. Typically, the global and regional projections, particularly the ones from the Hadley ensemble, they tend to be warmer and drier in summer and autumn than the full range of the UKCP18 probabilistic projections. This is quite an important implication, and we'll see some of the consequences of this later on. When we applied our UK CP18 projections, we used a relatively straightforward approach. We applied all the projections using the UK gridded observed data, and we applied these projections using the Delta method. So we've got 1981 to 2010 as our reference period describing the current climate, and essentially we just calculated changes and applied them to observed data using the Delta method. And this is illustrated in the figures on the bottom panel. So for example, this is one particular scenario for one particular location for one particular month. The blue line on the top panel is the UK CP18 projected change in temperature. That's a bit noisy, so we've smoothed that by putting the red line through. The bottom panel, the black line shows a repeat of the observed climatology if there were no climate change. And the red line essentially is the black line plus the red line from the diagram above. Now, that looks relatively straightforward. It's the Delta method. There are a series of assumptions involved in that, which we might want to pursue in discussion. And there are lots of reasons why we chose this method compared to other approaches. It has to be said that the application of climate projections to observed data is non-trivial. There are lots of technical challenges. It can be really complicated in order to apply it consistently across a large geographic domain. The different projections have different types of information. They're available at different resolutions. It's a non-trivial challenge. So although I've described method in one slide, this actually took up the bulk of the time of the project. Here's an example of some of our outputs. The indicator here isn't particularly relevant. So the top left panel shows impacts under the different forcings, different emissions scenarios. Top right is the same essentially, but using just those pathways that hit 2, 3, or 4 degrees. Bottom left panel shows the results you get from the individual global and regional models, but that's just for one level of forcing. And the bottom right panel shows how we've extracted the results from those previous analyses to show the indicators corresponding to particular levels of warming. And we've done that using what's known as the time sampling approach, where we just pick the time period where that target level of warming has been reached, global average temperature. So we've got these for almost all our indicators, and we've got this across n different geographic classifications and n different indicators and n different sets of projections. So you can see straight away we've got a massive information, and essentially what the point of the project is not to describe what these results are, but to provide results and information to users to allow them to infer what this implies for their particular policy areas of interest and so on. So because we've got n times n times n charts, I'm not going to show and present all those, and I'm going to provide 3 snapshots of results in a moment. And as a sort of like a trigger warning, the graphs on this will be very small. The point is not to see the details of the results. The point is to get some idea of the breadth of results that we've come up with in the project. So the first one, what we've plotted here is one particular region. This happens to be the Southeast England administrative region. We've plotted here all our indicators through time, mostly with the probabilistic projections. And in each case, ignore the bottom row for the moment, the red lines are the impacts under this particular set of indicators we get with the high emissions, that's the RCP 8.5, and the green is under the low emissions, and the yellow is the sort of intermediate one in the middle. And in each case, the range, the fuzziness around the lines represents our uncertainty in that indicator as we go through the 21st century. So I'm not going to talk about the specifics of this plot, apart from saying that the top row, in a sense, gives us the climate context. Second row has got some heat wave, cold weather type indicators. Third row has got some indicators relating to road and rail transport. Fourth row has got a series of agricultural indicators. Fifth row has got some wildfire indicators. And the bottom row has got some hydrological indicators. And these are calculated by CEH using the grid-to-grid model, which has been applied only with the regional and global models, not with the probabilistic scenarios, essentially because it'd be very computationally demanding, but the hydrological model uses information from across space, and the global and regional models provide that information, whereas the probabilistic projections don't. So this gives a snapshot for one region of these various indicators, how they change through the 21st century with different rates of emissions. And we've got this for different regions across the UK. We've got this at different spatial scales. So we've got this for particular local resilience for boundaries, for example, or for counties. I'm not going to talk about what these indicators tell us at this stage. Similar looking plot, this time it's just for the 2, 3 and 4 degree pathways. So same sort of set of information as before, but this time with worlds that hit different policy targets. Essentially extractions from those probabilistic projections we saw just now. The same set of indicators, same geographic arrangements, same variations over time. The third way of looking at our results is by level of warming. So here we've got, for the same region, those same indicators. This time we've plotted the indicator not against time, but against increase in global warming. And the vertical dotted lines are 1.5 and 2 degrees, just for information. And in this case, these are all indicators calculated using the regional climate projections. So again, I'm not going to talk in detail about these, about the results, just to point out that for some of these indicators, the relationship between global warming and indicator is relatively linear. For some of them, the relationship is highly non-linear. So some of them, the impacts increase substantially, then slow down. Some of them, they start off slowly and then increase. So we can't assume the linear relationship between increase in temperature and indicator. And impacts at 4 degrees aren't twice as bad as impacts at 2 degrees. They may be a lot more than twice as bad. They may be less than twice as bad. So 3 sets of illustrative results there for one particular geographic region. As I say, I'm not going to talk about what those results mean. What I'm going to do now for the next few minutes is talk about some key headline conclusions we've got from this sort of analysis. As I say, one of the points of the project is, if you like, to produce this atlas, to produce this set of information, but some high-level conclusions. There are 3 conclusions about what the indicators are telling us. The first one, is that, not surprisingly, there are very large differences in change in risk across the UK. And I've illustrated this by a couple of panels, one showing some metric relevant to transport and one showing an indicator relevant to fire. And the one on the left tells us that in the bottom right, or the south of the UK, the indicator tells us that things are going to get a lot worse to do with bad weather days on the railway through the 21st century. Whereas in northeast Scotland, they're going to get better. And that's because the relative importance of different components of this indicator vary differently in different parts of the UK. Southeast, the heat part is more important. The north is the snow part that's more important. And the relative importance of those 2 changes over time. The key point of this is that it's quite difficult to come up with large area averages that are particularly meaningful. So for example, the UK average change in railway bad weather days or UK average change in wildfire would not be particularly meaningful. The strong regional variability tells us that we need to look at sub-national scale results. That's a challenge for how we present our results. It's difficult to come up with a plot of the UK impact of wildfire, for example. The variability is very large. Second headline conclusion, and I'm illustrating this with just 5 indicators, is that actually some of these indicators increase really, really rapidly. increase very high levels. So the increase in risk can be extremely large, especially with high emissions. But also, we may see an increase in risk even with low emissions. So in this case, the green shows a pathway that's pretty much consistent with a 2-degree increase in temperature. Even then, we would see some impact. But the difference between the different rates of emissions can be really high. So this is like a warning that for some of these indicators, for particular sectors, climate change is going to have a really big impact on risk. And for some of them, that kicks in pretty early, and for some of them, it kicks in later. So in this particular example, wildfire, in a sense, not much happens in this particular place till, say, 2040, and then it really kicks off. So the change in risk can be really big. It varies from sector to sector. This in itself is not a surprise. We knew the change in risk is very large, but we looked at it across space, across sectors, with a whole range of consistent scenarios. The third headline conclusion is that actually, when you look to 2050, there's not a huge difference in impact in these indicators between different emissions pathways. So what we assume about the future rate of emissions doesn't make much difference for what we assume about change in risks to about 2050, which is a time horizon that's quite often used in developing climate resilience policies. So this begins to tell us that actually, if we're thinking about coming up with policies that are aiming to reduce resilience with a target date of, say, 2050, emissions pathways don't really matter that much. We need to think more about the uncertainty range due to natural variability and just our uncertainty in how climate change is going to manifest itself. 2, 3, and 4 pathways don't really make much difference to 2050. They do afterwards. The difference is really apparent afterwards. But timescale is really important. So 3 general conclusions related to the indicators. 3, what I've called conceptual or methodological implications. One is, well, what do we really think is a plausible worst case? RCP 8.5, which is the projection that's used as the sort of the top end in the UKCRP 18 projections, is actually quite high. It's got a big increase in temperature. There's a lot of discussion in some communities about whether RCP 8.5 is unrealistically high. That's a slightly different discussion, but is it really extreme? And how does it compare with what could be a 4-degree pathway, which is really quite plausible? And this panel here shows, again, for a particular location, again, for a subset of indicators, the difference we see in risk through the 21st century with high pathway, the RCP 8.5, and the 4-degree pathway. For some of the indicators, the RCP 8.5 pathway implies quite higher impacts or consequences than the 4-degree pathway. For others, the difference is less clear. So for the drought one, for example, there's not a huge difference between a 8.5 or a 4 pathway. But for the more temperature-related ones, then the 8.5 tends to give us higher impacts. So there's a discussion to be had about what we think of as like a worst case type of emission scenarios. And related to that is what do we choose from our estimates of impacts? So these 5 plots all include like the central estimate of change, but they also include the uncertainty range. So do we think about our worst case as being the top of the plume, the top of the shady area, or the middle bit? Those are, in a sense, are policy decisions, not science-based ones. So that's a point to discuss when coming up with estimates of how risk might change. What do we think of as the worst case? Is it 8.5? Is it 4? Does it make much difference what the 2 are? Is it the median that we use? Is it the high end from the probability distribution? And so on, and so on. Second thing that is worth thinking about is this, the difference between the Hadley Centre projections and the probabilistic range. The Hadley Centre range projections are at the top end, particularly for heat-related indicators, less so for the watery-related indicators, especially high flows, but it varies from indicator to indicator. But when we're using the regional and the global Hadley projections, and there's lots of good reasons why we would want to use those, then we need to be aware that the consequences, they're out of the range of one particular part of the probabilistic range. Again, it's difficult to come up with a sort of definitive scientific answer about what you should do, but we need to be aware of where the results using the regional and the global projections fit into the bigger context. The third conceptual and methodological issue is that when we've constructed our indicators, they're all numerical in the sense that they're numbers of days or the chance of exceeding some threshold, but we're not doing a risk assessment. We're calculating indicators which will be useful for those who might do a risk assessment. So for example, what I've put on this plot here are some boundaries where we might think are critical values, critical changes for a RAG rating, a red, amber, green type rating. So what will be a red impact? What will be a green level of impact that we're not too worried about? What will be an amber level that we're a bit concerned about, and so on. And those indicators, those lines, those threshold values can't be defined scientifically. They're based on policy decisions. So for example, when we look at the rail network risk indicator, details aren't important, would a green risk be that threshold, that number doubles, or would a green risk be that number increases by 5%? That's a decision for policymakers, for people who use this information. But the point is, we can use these indicators to inform risk assessment by coming up with threshold boundaries to identify red, amber, and green ratings. We haven't attempted to do this in the project because we, as the scientists doing the project, don't know what these critical values relevant for these indicators are. Is it a doubling? Is it an increase of X? That's dependent on the policy community. So the information is a contribution to help inform a risk assessment. Coming up with those boundaries between red, amber, and green levels of change is a policy decision. Okay, so that's a rather rapid canter through the project. Hopefully I've given a flavour of the sorts of indicators that we've constructed. Just to remind us of the three headline conclusions. The change in risk varies across country, so large area averages may hide lots of useful information. The change in risk may be extremely large for some indicators. There's not much difference in risk to 2050 across different emissions pathways. That might be relevant when we're constructing different visions of what the future might be like. And there are a series of conceptual issues which have been highlighted by the way we've calculated and had to construct these indicators, to do with worst cases or where the Hadley Centre projections fit within the bigger range, and how we can use this information in the next step in risk assessment. So that's all I want to talk about at the moment. The project is nearly complete. We're constructing the project report and appropriate papers as we speak. One of our big challenges is to work out how most effectively to present and provide N charts times N regions times N indicators, etc., etc. And we're looking at developing a web-based web interface to allow you to access these results. And we'll put information about where that might be on the project part of the Climate Resilience website. Thank you very much.